Today we're going to look at quadratic applications. Our objective is to be able to use a graphing calculator to answer questions about quadratic application problems. We're going to look at three problems today. The first one is our bathtub problem. And it says the number of liters of water remaining in the bathtub and the number of minutes which have elapsed since you pulled the plug can be represented by the quadratic equation v of t equals 2.4 t squared minus 24t plus 60. Hopefully you remember this is just function notation, where this says we're going to get volume if we input time. So if I know how many minutes after we've pulled the plug, it'll tell you how much water is left in the tub. So there's three things I'm asking. What are the domain and range restrictions for this problem? How much water was in the tub when you pulled the plug? And when will the tub be empty? I'm going to hold off on part A until the end, so I think you'll understand a little bit better. But the first thing we want to do is take our calculator, okay, and go to y equals and type in our equation. Now I have the three equations we're going to deal with today, but I have those turned off. So I'm just going to graph this first one. And again, it says t for time, but we're just going to use x for our calculator. I'm going to hit zoom 6 so I get my nice graph, and this is what it looks like if we use a 10 by 10 graph. Now if you notice, I can't see my three important parts: my x-intercepts, my vertex, and my y-intercept. I can see possibly vertex and x-intercepts, but I definitely can't see my y-intercept. And if you remember from our standard form, y-intercept, like always, is when you substitute 0 in for our t, or our x in this case, and then we get our c value, our 60. Well, I can't see that because I'm only, if I look at my window, I only went up 10, but I definitely want to go up at least 60, so I'm just going to go up a little bit higher than that. I'm going to hit 75. I'm going to let it graph, and now this is what my graph looks like. I'm just going to plot it over here. Okay. Now if you notice, I only kept the first quadrant. Now I know I said I was going to get to domain and range in a second, but when we're dealing with real-life problems, typically our variables are things that we do not want negative. So here our x is our time, so this is time in minutes, and we don't want to talk about negative time. Okay, negative time would mean time before you do something, and if we're talking about a problem, why do I care what I did before it? In this case, y is our volume, and that's in liters. Okay, so I can't have negative liters, I can't have negative time, so that's why we're stuck in quadrant 1. So now if I look at what's in quadrant 1, I go from here, my y-intercept, all the way down. But let's think about what's happening. Okay, we have so much water in a bathtub. At time 0 is how much water is in the tub, and as time goes on, after I pull the plug, we start to get less and less water in the tub until our volume hits 0. Okay. Now, if you notice, the graph goes back up again, and it says it's modeled by a quadratic. But in real life, does it make sense that if you pull a plug and the water gets empty, that the tub is magically going to fill up again? Well, it's not. So we actually get rid of all the stuff past when the volume is 0. So our domain is really stuck from time equals 0 until whatever time the tub is empty. Our range is the y. The highest our y gets is when the tub is completely filled. The lowest it gets is when it's empty. Okay, so if we want to talk about this, okay, our range and our domain, the range is a little bit easier. Okay, the range is our y, our volume. Well, we know that our volume, okay, I'm just going to put a v for volume, is between, has to be greater than 0 or equal to 0 and less than or equal to 60, because that's right here, our y-intercept. Our domain, well, is our time, and we know that time can't be negative. Now, even though we stopped here, I don't know what this answer is yet, so I can't put anything there, but I definitely know that time can't be negative. So we can say that time has to be greater than or equal to 0, because time can go on once the tub is empty. Okay, it would just mean I'm sitting there with an empty tub. So how much water was in the tub when you pulled the plug? Well, when I pulled the plug, that would be at time 0. So at time 0, there's 60 liters in the tub. Okay, it's what we started with. And now I want to find out how much water is in there when it's empty. Now there's a couple ways to do this. You can hit second trace and use 0. That's your x-intercept. But remember, I talked about a different way. And the other way is, well, if I want to x-intercept, or if I want to talk about this, I want to know when there's nothing left in the tub. And I don't want to get rid of my other equation, so I'm just going to move down to y4. If the tub is empty, that means I have a y value of 0. So I'm going to make this equation a little bit darker so you can see it when I graph it. That's when the tub is empty. If I want to know when this graph equals 0, I can just find the intersection point between these two graphs, and that's another way to do it. And then what I'm going to do is move my cursor close to where they intersect and hit enter 3 times. 1, 2, 3. And it's going to tell me it intersects at, when y is 0, when the tub is empty, at about 4.999 repeating, which is about 5 minutes after the plug is pulled. Okay. And that's the answers for that problem. Let's go on to our second example. The car insurance problem. A car insurance company offers a senior citizens accident policy. You know that the number of accidents per 100 million miles driven should reach minimum and then go back up again. Therefore, the model you predict is A of t equals 0.4t squared minus 36t plus 1,000. Okay, so if we look at this, A is our accidents, and t, okay, for this problem is going to be, and I know they didn't really mention it, but it's our age. Okay, so accidents per million miles driven. So as our age goes, that's the number of accidents. So what is the domain and range restrictions? How old is a person who has 350 accidents per million miles driven? Based on your model, who is safer, a 16-year-old driver or a 17-year-old driver? And who appears to be the overall safest driver? So again, I'm going to go to my graph. I'm going to turn off the equations I don't care about now, just by hitting enter on it. And then I'm going to turn on our equation for this problem. So our equation for this problem is our 0.4x squared minus 36x plus 1,000. Now again, I just have my graph from my last one. Let's see if I can see anything. Well, I know that I have a y-intercept of 1,000, so I know I'm going to change my window. I only went up to 75, so that makes sense that I didn't see it. So if I have a y-intercept of 1,000, again, we only care about the first quadrant. We only care about positive accidents. Can't have a negative number of accidents, and your age can only be positive. So I don't really need to go much further up than this. But since it's in thousands, I'm going to go up 1,500 and hit graph and see what I can see. So this is a really wide parabola, so I need to go way further to right, and I'm not even to the vertex, so I know I'm going to have to go more than double. And let's think about what the x represented in this graph. It represented the age of the driver, so it makes sense to go higher. I'm going to go up to all the way 100-year-old. Now hopefully someone 100 still isn't driving, but I'm going to put that in so I can see my graph. That's why it's always really important to know what your variables stand for. This is time, or our age, okay, and this is the number of accidents. Okay, so t is usually time, so in this case it's time you're alive, so our age. So if we notice here in the first quadrant, we get a graph that looks like this, which should make sense. Okay, as you become a better driver, the number of accidents you have go down, but as you get older and older, you maybe start to, your reflexes go down, your eyesight goes down, hearing, and the number of accidents you have go up. So let's see what we can answer about this. Again, if we ask the domain restrictions, so if we think about this, again, we care about the first quadrant, but in real life, you can't drive until you're what, about 16. So it only makes sense that your age, okay, or your time has to be greater than or equal to 16 years old. Now you might say, well, you can get your permit earlier, but we'll just talk about 16 as getting an actual driver's license and having your car insurance on you. Now if we talk about the range, okay, the number of accidents, well, in our picture, okay, there's a minimum. Now, if you think, well, not every person in the whole wide world has an accident, but remember, this is per 100. This is number of accidents per 100 million miles driven. Most of us aren't going to drive 100 million miles. So, we're going to go from down here all the way up. So from here, and again, you can go up forever. Some people have a lot. So, again, we have a minimum. And again, I don't need you to put an actual number here. I just need us to kind of talk about and understand what these are. Technically, you could have 0 accidents. I think in this picture they don't show anyone, because if you drive that much, the chances of you having 0 accidents. But our range would go from here, our lowest, wherever our low part of our vertex, and it would go up forever. Okay. So the next question says, how old is a person who has 350 accidents per million miles driven? Well, this is a y value, because that's our number of accidents. So if you remember, we're going to go into our graph, our y equals, and I'm going to type in 350. It's already in million miles driven, so I can just type in 350. I'm going to hit graph, and I should see this horizontal line drawn. So if I notice, it hits my graph twice. So there's a younger age and an older age that have 350 accidents per million miles driven. So again, I'm going to go down to my intersect. Okay, since there's 2 intersection points, I need to move my cursor closer to one of them. Hit enter 3 times. And it gives me an age of about 25 years old. And if I go to the other point to intersect, I'm going to scan all the way over here. And hit enter 1, 2, 3. I'm going to get 65 years old. So 25 years old or 65 years old. Okay. Based on your model, who is safer, a 16-year-old driver or a 7-year-old driver? So remember, those are my X values. So I'm going to go back in. I'm going to get rid of this Y value so I don't have to worry about seeing it. I'm going to go back to my graph. And 16 is an X value. So if you remember, I'm going to hit second trace, and I'm going to put in a value of 16 years old. And that tells me a 16-year-old has about 526.4. Okay. So we have 526.4. If I go back and hit second trace and do value and put in a 70-year-old, they have about 440. So if you look at this, they're saying that who is safer, 7-year-old is safer, okay, because they have less accidents per 100 million. Okay, it's less accidents. So who appears to be the safest driver? Well, the safest driver would be the one who has the least amount of accidents overall, which would be our vertex or our minimum. So again, if we go into our graph, I'm going to hit second trace. I'm going to find the minimum. I'm going to move my cursor close to it. Now remember, I showed you a couple other ways to do this. I could just go to the minimum and think, well, I want a number less than this. What's a number I know for sure is less than that? I'm going to hit 30. And a number I know for sure is less or greater than 45, I'm going to hit, say, maybe 55. And I'm going to hit enter. Remember, you can go left or right or pick a number you know for sure is to left or for sure is to right. So my minimum is at 44.999 or 45 years old, because they only get 190 accidents per 100 million miles driven. So this is 45, 190. So the safest driver would be my 45-year-old. Okay. So let's go on to our last example, the football problem. And you're going to see more problems that look similar to this, but we can give you an array of problems. So when a football is punted, it goes up in the air, reaches a maximum altitude, then comes back down. Therefore, a quadratic function is a reasonable model. So if you look here, we have h of t equals negative 16t squared plus 40t plus 4, where h of t is the height of the ball after t seconds in the air. So as soon as we kick it, as soon as the time starts going, this will tell us how high the ball is. So again, I'm going to go to my calculator, go to y equals. Okay, I'm going to get rid of some of these old equations because I don't need them. I'm going to make sure this equation is turned on, and then again, I'm just going to hit zoom 6 to start over again, because I've changed the numbers. So here it shows the ball going up and coming back down. This is 10 by 10. If you notice, it didn't take very long. The ball wasn't in the air very long, but I need to go up more. So I know my y-intercept is at 4, but I've already passed that, but my vertex is higher. So let's say, I don't know, 40. And I can see it. The ball goes up and comes down. Again, this isn't how far it's kicked. This is time. So if I look at this problem, this is time in seconds, and this is height. Okay, and I believe they said feet. I think they said feet. Okay. I don't think it said feet, but this is in feet. Alright, so I want to know what are the domain and range restrictions for this problem, how long did it take the football to hit the ground, and what is the maximum height of the football. So if I graph this, I know it started at 4 and went up and came back down. If I talk about the domain, well, I care about when the ball was kicked to when it hit the ground. Now again, time can keep going on forever, but that's the time I care about. But again, as long as time is positive, we're still okay. The range would be the highest the ball goes all the way to hitting the ground. So you could make it simpler and just say, well, the height of the ball has to be greater than or equal to 0. Since I don't know how high it is, it's going to eventually stop, but we know for sure the height can't be negative. Now, again, these could always be more specific, but we'd have to do some of the problem to actually figure that out. How long did it take the football to hit the ground? Well, I'm looking for time when it hit the ground, which means I'm trying to find my x-intercept. Again, I'm going to do it the other shortcut way. I'm going to put in 0 for y. I'll do a darker line so you can see it. I'm going to hit graph. So this is when it hits the ground. I kick the ball, it goes up, and it hits the ground down here. So there's 2 intersection points. This one's actually a negative time, but I care about the positive time. So I'm going to hit second trace, number 5. And what I want to do is move over to be closer to that one. I'm going to hit enter 1, 2, 3. And I find that, again, remember, this is as close as 0 as we can get. This still means 0. At about 2.59 or 2.6 seconds is how long the ball was in the air. That's our hang time. So how long to take the ball? 2.6 seconds to hit the ground. What is the maximum height of the football? Well, I'm looking for the y value, height, right here. So if I go to that, I'm going to hit second trace. This is now a maximum as opposed to the last problem that was a minimum. Okay, I'm going to have to move back and forth. Here's about where it is. Again, if you want to do the left, you can hit left a few times till you're on the left side. Go back, now hit right a few times till I'm on the right side, hit enter. I get 2 numbers. Now remember, the first one is my x value, my time, so that's how long it took to get to the height, and then the y is how high it goes. So this one, the highest the ball gets is 29 feet. Okay. I hope you feel a little bit better about solving some different application problems using your calculator.